Hello YouTube, back again after a few months. I haven't made a video for quite a while, and well, I've just been lacking motivation in general, but for making videos in particular. I've got a number of things I still want to make videos about. I've picked up some interesting items of junk recently that I'd like to open up and show you, plus a lot of old retro computer gear, and just got to get around to doing it all. Anyway, one of the things that I've been distracted with since the last video was a software project, but also this GPS disciplined oscillator. It's just the beginnings of it. This video is not about that, but I will be using it in this video. This video is about this thing over here. Let's have a closer look at it. It's a Hewlett-Packard 3330B Automatic Synthesizer, which basically produces sine waves, and in what I reckon is probably the most complicated way possible. We'll see more of that when we get into it. I tried to start this video ages ago. Every day I've been telling myself I must do it, and well, today's another attempt. I did an earlier attempt a few months ago. I might use bits of footage that I recorded then, and I also discovered I had some much earlier footage of this thing when I first got it, and may incorporate some of that as well, which will explain why this 7 button isn't there. I should mention that the 3330B is often accompanied or often teamed up with a 3570A network analyzer, which I also got with that. I've done nothing of this. I don't have much interest in it, at least not until I find out more about it. So yeah, just saying you'd often find these two together. I may do just a quick teardown and look inside this thing at some stage, but for the moment I've only been concentrating on this guy. It produces sine waves out this hole here, and they can range from, I believe, 0.1 Hertz to 13 point something megahertz with a resolution of 0.1 Hertz. It can also sweep the frequency through a range, or it can sweep the amplitude through a range, but not both, only one or the other. And we'll have a look at that in a moment. This video may be a bit of a hodgepodge of the bits of other video I've done, so it may be a bit disjointed. I hope it comes out alright. When I first got this, there was some trouble with the displays. I'll show you that here. Frequency 11111. Clearly something wrong with those two digits. Frequency 222222. Yeah. And that just turned out to be, the displays are actually 14-pin dual inline packages that just plug into IC sockets, and they're a bit sloppy. There might have been a bit of corrosion on the pins, and they just needed to be reseated, and everything came good there. This thing here had me tossed for a long time. I didn't know what the hell that was. Finally, somewhere in the manual, I think I found that it's used to release the keyboard so that it can be turned out at different angles. I'm not sure what the point of that is, because the display doesn't change angles, so what's so good about the keyboard doing it? And I also think that it's supposed to spring out. Like when you do this, it's supposed to spring out. And so there shouldn't be any need to grab things as I did there. After I discovered that, I wondered why it didn't have some sort of a handle to pull it out, but I believe it's supposed to spring out. Well, I haven't done anything about that. When I took these keys off to clean it, I managed to break the little tang that sticks out of the main stem into the key itself, and to repair that I've just got a loop of wire and melted it into the stem, so this is acting as the missing tang. But the 7 key didn't grip it quite as well as it should, and it's fallen off somewhere. It's around the place somewhere, I just haven't found it. I will eventually locate it and put it back, but for the moment we can still go to 7 by pressing that. Let's turn it on and look at what it does with an oscilloscope connected to the output. Alright, we'll turn it on. It's in standby. It's had power applied. Standby keeps the oven controlled crystal oscillator warm, and it draws about, I think I recall it being about 3 watts in standby, and then if you come in from cold it's about 17 watts until it gets the oven up to temperature. I forget what it was when the thing's actually on, but we'll turn it on. It's quite noisy. The fans take a while to come up, and And then I've got a bloody noisy oscilloscope as well, although you can't hear it much over this. Okay, so to get a frequency out of it, you go frequency and you type in the frequency you want. Let's put in 1 megahertz, and then you have to set the output level, amplitude 1 dBm, and there's our sine wave. A bit of glare there, haven't we? And 1.00005 megahertz. So according to the oscilloscope, it's a bit more than what it claims down there. Let's we can go up. Well, the limit is 13 megahertz frequency. Well, 13 point something. I forget exactly what. But again, it's reading a bit high, 0004, but only in the last digit. You can go to frequency 1 megahertz, and again, a discrepancy in the last digit. Let's go down to 100 kilohertz, frequency 100 kilohertz, and now we've got a discrepancy in the not last digit. So it's saying we're about 20 hertz high, 10 kilohertz, and again it's saying we're 20-30 kilohertz high. So that seems to be a consistent discrepancy. Now, is this wrong or is this wrong? And that's why I've got the GPS to confirm. What are we at? That was 10 kilohertz. Let's go to 1 kilohertz. Here we're well away from that last digit, so it doesn't look like an error in the oscilloscope. 1.02, so it's 20 hertz too high again. Dropping frequency down even further. Frequency 100 hertz, and it's saying we've got 120, 130. So it seems to have this consistent 20 hertz too high, according to this oscilloscope anyway. But we'll come back to that. Let's play with these sweeping functions. You've got to have a good think when you're doing this. If we say frequency 5 megahertz, and we want to sweep, say, from 0 to 10, so that's, we've got to say frequency step. How many steps do we want? If we want it to be smooth, we can have 10, 100 or 1,000 steps, but let's make it 1,000 steps. So now we've got to sweep 5 megahertz either side of 5 megahertz from 0 to 10. So our 5 megahertz divided by 1,000 means our frequency step is 5 kilohertz. And do we have to halve it because we're going either side? I'm not sure. Let's put in frequency step 5 kilohertz, and then start continuous, and you can see the frequencies. It doesn't show it on the display, but you can see it here. We can also control the speed of it, so we can say make it very slow, number of steps per second, so it's only changing very slowly, or we can speed it up, and with the frequency you can speed it up more than you can with the amplitude. And now it's going very fast, and the oscilloscope doesn't show it properly, so I might switch to an analog oscilloscope. Shows it better. Right, on this poor old thing, to get it to work at the highest frequency range, I have to turn the brightness up a lot, otherwise, yeah, could do a repair on this thing too, but for the moment. Okay, now if we go frequency 5 megahertz, we're going to have 1,000 steps, and we want to sweep from 0 to 10. So the range has got to be the full range I've worked out, not just one side. So we want to go 10 megahertz sweep. So the frequency step is going to be 10 megahertz divided by 1,000, which is 10 kilohertz. And now we start the sweep, continuous. That, you see it jitters a bit at one point there. If I switch to a lower range on the oscilloscope, it doesn't do that, so it's just an artifact of the oscilloscope, I believe. So we're going pretty much from 0, we can slow down the sweep speed, that's the fastest. Now we'll slow it down. And you can also say whether it does sweeps both upwards and downwards. Here we switch to down. I think it'll start when we get to the end of this cycle. So we'll speed it up again. It starts off with a high frequency and slows down, immediately returns to the high frequency and slows down. That's sweeping downwards. If we change it to sweeping upwards, it starts off with the low frequency and sweeps up. When it gets to the top, it starts from the low frequency again. And you can just do a single sweep, and I think if you're doing single sweep, stop, yeah, if you're doing a single sweep it does show the frequency on the display. So we're getting up to about 10 megahertz there. That's just a single one. Let's do another single one. Bit hard to tell. I'll let it go all the way through. Started off with a slow speed, slow time per step. Start again single, and we should see this start from around about 0 hertz. It's going up by 10 hertz at a time. Bring that up a little bit. Yes, it's been a reliable old beast, but I've abused it a lot, and yeah, it did fail once many years ago. I replaced a diode in it, probably with the wrong diode, and yeah, it could do with a revisit. Anyway, speed it up a bit more. Nice sine waves. And let's try the amplitude sweep now. Let's stop that. We'll go to a lower frequency. Let's make it frequency 1 megahertz, something the Hung Chang can deal with a bit better. Now I can barely spell dBm. Let's go amplitude, let's make it 1 dBm, and amplitude step. Now let's make amplitude 10 dBm. And amplitude step 1 dBm, and sweep that. You've got to switch it to amplitude, of course. Sweep that. Is it doing anything? Out of range, dirt. Okay, amplitude 5 dBm, and amplitude step 1 dBm, and sweep out of range again. What am I doing wrong? Back in a sec when I work this out. Yeah, I had stepping 1 dBm and wanting 1,000 steps makes it get past the 13 dBm limit in a big hurry. If I change it to, what have I got now? Let's stop it. We've got 5 dBm per base, and amplitude step is 0.01 dBm. So let's start that now. You see it gradually getting bigger. So 1,000 steps is probably a bit too much for the amplitude. I'll switch it to 100. So now it's stopped again. We've got to restart it. Happens a bit more quickly now, but doesn't change so much, of course, because we've only got 100 steps. So let's change the, instead of 1,000 steps at 0.01 or 100 at 0.01, let's make it 100 at amplitude 0.1 dBm. Sweep. Yeah. There we go. And we've got it only sweeping in one direction, so put it on both now, so it goes up and down. Now I've got a 50 ohm terminator on that. It's a 50 ohm output. As I say, I can barely spell dBm, so calculating what the oscilloscope should be measuring, I don't think it's producing the right value, but I can't, I'm just not familiar enough with dBms and that stuff to prove it, but I think it's not putting out the right value. You can look up charts that tell you, dBm to volts with a given load, 50 ohms, and yeah, I don't get, according to the other oscilloscope which can measure it, I don't get the right values. Let's try playing with some audio. Now with the Brulin Care power amp going into this speaker, 1 megahertz is probably a bit high. Let's go down to frequency 5 kilohertz and amplitude 1 dBm. and sweep it 2 kilohertz either side of that. So that's a 4 kilohertz sweep divided by 1000, going back to frequency sweeping, divided by 1000 is a 4 hertz frequency step. 4 hertz frequency 2 kilohertz. Sweeping now. Should have got up to about 1000 steps at 4 hertz is 4 kilohertz sweep, so that should have gone up to 4 kilohertz, and now it will come down to 0 hertz. Yeah, anyway, that was just a bit of fun. What I really want to do now is check out that frequency error of 20 hertz. It seems to be 20 hertz too high, and the way I want to do that is by, with the analog oscilloscope, measure this on one channel and the output of the GPS disciplined oscillator on the other channel, and see if they are the same frequency on the oscilloscope, and or see what I have to adjust this to make them the same frequency. Right, looking at the output of the GPS DO, it's well within a hertz in the long term, as you can see up there, and even in the short term, just second to second, it's within usually 1 hertz. Ignore that, that's just a glitch, but it's within 1 or 2 hertz of 40 million every second. So this is well within 1 or 2 hertz, even just second to second, and which is more than sufficient to tell if the HP synthesizer is out by 20 hertz, which is a lot more. Now, this GPS DO, as opposed to most, which produce 10 megahertz, this one produces 40. So that's what this divider here is about. It's just a 32-bit counter. We're sticking 40 megahertz in, happens to have a few LEDs on it, and we're picking off a few of the very low frequency outputs from the divider. But here is the second output, so that's dividing by 4, because the HP can't go to 40 megahertz, we have to bring this down to 10, which that can do. So on the oscilloscope we'll get that 10 megahertz input on one channel, and we'll tell the HP to put 10 megahertz on the other, and let's see what they look like. Right, there's the two signals. Bottom one is from the HP, the top one is a pretty distorted square wave coming out of the divider, because I haven't got any termination on that signal, but good enough. Now the oscilloscope is currently triggering internal, which is sort of a mixture of both of those, which is why we're getting some sort of stability. But if I switch to just channel B triggering and trigger off that, not the same frequency. So what do I have to change this to make it the same frequency? Now if I go frequency step 1 hertz, and then you can change the frequency of this, and it's changing very quickly because I've got the time set up fast, so I'll turn that to slow. I would have thought if I make it 20 hertz short of 10 million, that should compensate for the 20 too much. Doesn't seem to be working. Right, I have had this experiment working before, and I found that if I reduced it from 10 megahertz by about 20 hertz, I could get these two to synchronize, and it's not happening. So if I make the frequency step 0.1 hertz and set the times per step quite fast so that it repeats quickly, and then zoom down, watch that bottom trace, make it even faster. So just slow it down so I can home in on. Oops, wrong way. Nearly there, and we go locked there. We go one more, just two parts, so pretty close there between those two. But I've had to come down, what's that, 370 Hertz, which is a lot. And if I take off different tappings on the divider, so now we go to the 5 megahertz tapping. We're getting 2 cycles of this per that, so we change the frequency of this to 5 megahertz, and then we have to speed this up and try and get down to a fix. Yeah, so about there. And what are we down there? 170, less than 5 megahertz. I've done this right down for 7 sets down to about 150 kilohertz. Whereas before there just seemed to be a 20 hertz offset. I could go down to the lower frequencies, and I only had to come down 20 hertz, and I got close to a lock. But now there seems to be a scaling and an offset. So I recorded the values that I had to put in here to get close to locking, and stuck them into a linear regression analysis calculator, just something online, just put in the 7 sets of values I had. Here's the values I got, the standard frequencies coming out of the divider from the GPSTO, and the frequency I had to enter on the HP to get the 2 waveforms to be almost in sync. There's the difference, and you can see it's no longer a constant 20 odd hertz. Looks like a bit of scaling error has creeped in, and if I stick these 7 pairs of values into linear regression calculator, it came up with this, a slope of, this one says 1.000, so almost as it should be, but there's this constant offset of 18.6 something, and in another one those same values produced this 0.9999, so that's the very slight scaling error, and again 18.6 offset, which is, you know, around about what I might have seen last time. So this here, that might just be they might both be just calibration of the HP, but this bit here is just, that's a bit too much, don't you think? This bit seems pretty close. Maybe calibration's all needed there, but this seems suspicious. Hopefully it's just calibration as well. Find out more once I understand this thing a bit better. Alright, so I'm sure you didn't want to see all this stuff. You want to see what's inside this, so let's open it up. Okay, here she is. I'll remove these 4 screws here to get the lid off, and I'll also take these 2 out to get this off so we can look at those displays. Alright, that's pretty easy. And you can see these displays are just like ICs, except the pins run across the short end instead of down the sides, but yeah, they just unplug, and I believe that my problems at the beginning were just that they weren't seated properly, and a bit of oxidisation on the pins, and I've noticed it's started to happen a little bit again, so I might have to put some deoxide on them. Alright, and under the big lid you can start to see why this thing weighs 22 kilos. There's a lot of aluminium in there and a lot of circuit boards and many holes for adjustments, so yeah, it's probably even surprising that it's even as close as it is in frequency output, so maybe there's a lot of room for calibration here. Anyway, I'll take these plates off and we can see more of what's underneath them. So there it is, with all the plates off, and there's a lot there, isn't there? When I first opened this, I was immediately reminded of something I'd seen decades earlier when I was like, 12 or 13 at an exhibition. It was one of these. a Digital Equipment Corporation PDP-8S mini computer, and the one I saw also had its lid lifted up like this, showing all the circuit boards in it. And this thing, with all its circuit boards, immediately reminded me of that. Of course, most of the things that at first glance might appear to be circuit boards are actually aluminium bits separating the compartments, and there you go. There's why it's so heavy. There's so much aluminium in there. So most of these compartments have only one board in them. This is obviously a more digital section which doesn't need the shielding as much as all this, which is presumably analog, more analog. And the superficial similarity to the PDP-8S mini computer is actually, there's a bit more to it than superficial similarity. Turns out this is a digital computer. No microprocessors, it's all done in 7400 series TTL logic. But yeah, there's a digital computer in here. We'll see more of that as we go on. As you can see, every board just about has its own compartment, and these seem to be a sort of a modular extrusion that can be plugged together. They're separate pieces that can be plugged together. They're just like a U shape. And there's these tie points for stability, rigidity, and or electrical grounding. When I first got this, it was set up so that the output came on one of these rear terminals. I disconnected that and plugged this one on, which goes to the front terminal. Okay, let's have a scoot over the top of the thing. Power supply boards. Presume there's a transformer under there somewhere. That, I'm pretty sure, is the oven controlled crystal oscillator. A lot of gold plated circuit boards there. They all seem to have their function written on them, so that's nice. Shall we pull a few out and have a look? Yeah, let's shall. Starting up the back. Oh my god, look at that. A lot of gold there. This is the reference sampler. Beautiful. Very, very nice. I just should have looked at the power supply boards first. Even the power supply boards covered in gold. And a bunch of nice test points, adjustments. There's the other one. Now I know that some of these boards, some of these boards are identical, so they could be a help in troubleshooting by swapping them over. That's the VCXO cont, whatever that means. Variable trimmer capacitor, very nice. This is N1 VTO. A lot of test points down there, but not much use down the bottom, are they, unless you've got an extender card. And I don't think we get a free spare one in here. Counter sampler. Okay, I think we're number 2, 3 VTO. We might be just repeating ourselves now. Next column. Lots of adjustments, so yes, all my suspected errors in its output could be down to adjustment rather than an actual failed part. Now there's a lot of gold area. That's SL1 mixer. SL1 phase detector. This is electronics porn, isn't it? Bloody beautiful. And I think these are just repeats of that. Over to here. That's a big polycap. SL2 and 3 mixer phase detector. That's a pretty wide finger. He's got a switch on him too. Huh. Yep. He's got a cable. Can you see that? Relay. A transformer or another sort of relay. Not sure. Not sure what that is. Another relay there. Another switch. Relay. Amplitude modulator. Output mixer. And he's got a switch too, and a socket with nothing going to it, and there's no cable down the hole that should go to it. This one's hard to get out. I'm not sure if I can get that out without breaking something. Let's a quick look at the top of it. Oh fucking hell! I just broke my camera. Oh well. Bloody hell. Yeah, that's not coming out easily, so there seem to be 3 boards with this plate, and the plate goes to the ejectors, but I can't get enough leverage without feeling like I'm about to break it. And there's the last board. And that doesn't seem to have any ejectors at all, or no, it's bolted onto this, so that's a fairly big assembly. Maybe I could lever it out with screwdrivers, but I don't want to try that at the moment. Got enough busted stuff here at the moment. So a few large electrolytics, which may or may not be any good. So I suppose what I'll do next is, I won't do it in this video, but I'll go over the power supply, check the voltages with an oscilloscope to make sure there's no excessive ripple indicating a bad cap. Maybe try and see what's coming out of that oscillator, see if that's the source of my 20 hertz extra that shouldn't be there. Oh, we didn't look at the digital boards. Okay, how can I do that with a broken bloody camera? I've busted the mount on my camera, so I can't put it on the tripod anymore. So we'll have a quick look at these digital boards. This one's missing an ejector on one side. Get this one out first. And it's got 4 IC sockets across the top, which go to nothing, so I wonder what they are. Bodge wires, but nicely covered with glue to protect them. One chip there has got a socket, and there's a couple more over there too. And those sockets might be put there as part of the Bodge ECO. And one more, which goes to the front panel obviously. Oh yeah, pretty easy. 74199, which are not sure off the top of my head, but there's quite a few of them. So 74199, 74100s, mostly 74100s. I'll look them up. Okay, so I think that's every board except the front panel. I won't get that off. There's the displays. I'm not going to take this off. I think I remember that being a pain in the ass. There's another circuit board down there as well as this one at the top. And a quick look at the bottom. There's the instruction sheet. You pull back the holder. So every pin's is labelled on the PCB. This thing was really made for servicing, I think, with all the test points, with all this, the ability to pull out individual cards, maybe put them on extenders, swap a few of them around. Yeah, it seems to be made for servicing. Let's see, there's all the power supply section, capacitors, so yeah, very nicely made machine, this thing. And let's have a look at the back now. And on the back we've got a air filter. I don't know if you can put maybe there's some sort of cloth fabric thing that can go in there for finer filtering, or maybe not. Various labels, lots of B and C connectors, reference oscillator internal and external, so we can feed an external in, which ultimately will be my GPS DO reference tune. Maybe that's all I have to do, twiddle that, who knows. This is an HPIB interface, optically isolated. Cute little IEC connector. You can't get to the fuse unless you pull the plug out, and there's a little lever that lets the fuse out, and underneath that there's a little circuit board that selects either 230 or 115 mains voltage, and a missing option something or other. Yeah, alright, now let's have a look in the manual and see if we can understand how this thing actually works. Right, how does this thing work? This is me trying to explain. I won't go into any great depth because my understanding is only pretty basic. But there's two main sections, of course. There's the frequency synthesis section, and then there's the digital internal computer control section. We'll look at the frequency synthesis first. Here's a block diagram of that. Now, this is not from the service manual, it's from the Hewlett-Packard Journal from July 1972. There are 7 phase lock loops in this thing, 4 down here and 3 up here. These ones are called divide by n loops, and these top 3 are called summing loops. This technique, by the way, is called indirect frequency synthesis. Now we have the 20 megahertz reference oscillator. That's derived from the oven-controlled crystal oscillator in the back corner of the unit. I think that generates 5 megahertz and it's turned into 20 megahertz, and that goes into the output, and I believe that's where my problem might be. All this stuff generates down here, generates a signal. Here's an example to generate 11 point blah 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 megahertz. The output of all this is 31 point blah 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 blah, and it subtracts the 30 megahertz by mixing it with that, and the difference is the output signal. Now if that 20 megahertz is off by just 20 hertz, then this will be off by 20 hertz. So I think that explains my problem. I might have to do nothing more than just twiddle that little reference adjustment control on the back of the unit, which I'd completely forgotten about. Anyway, so that signal also goes into a divide by 200 to come up with a 100 kilohertz reference signal that goes into the 4 divide by n PLLs, and each of those takes 2 or 3 digits from the frequency to be generated. So in this example of 11.12 blah blah blah, the top 3 digits go into this PLL, the next 2 here, there, and the least 2 significant digits go into this one. Now, this one having an extra digit, it doesn't have to handle 10 times the range of the others because the top digit can only be a 0 or a 1, so double the range perhaps. Now these generate a signal that's this value times 100 kilohertz plus a base frequency of 20 megahertz for this one, and for the other 3 it's 19.8 megahertz. I don't know why there's that difference between them. Into this goes 44, 100 kilohertz times 44 is 4.4 megahertz, plus 20 gives 24.4 megahertz. so on and so forth. But take the top one, 111 times 100 kilohertz plus 19.8 gives 30.9 megahertz. And those values, well, the least significant one, gets divided by 100 and goes into the first summing loop, where it gets added to the frequency from this PLL. The result of all that gets divided by 100 and added in the next summing loop with this frequency. Then that's divided by 100 and added to this frequency. So you can see this frequency doesn't get divided, it comes out because it's the most significant, whereas the lowest two get divided by 1,000,000, 100 3 times. So we have a look at the details of these things, to understand how these guys work. The summing amplifier, summing loops I am a bit more hazy on, but the divide loop looks like this. The two BCD digits, or 3 in the case of the topmost one, go into a D to A converter to produce a voltage proportional to that value, which gets added to this and controls a VTO, voltage tuned oscillator, or VCO, voltage controlled oscillator, and that produces the output of this stage. It also goes back to a variable modulo counter, which divides by that same value presented to the DTA. It divides that output by this, and that should be 100 kilohertz if everything's working properly. And it compares it to the 100 kilohertz reference, which is the signal along the bottom that's going into all of them. And if that's 100 kilohertz and it's equal to the reference, then there's zero adjustment value to the VCO. If there's a difference, it adjusts the VCO, and the result here is it will get adjusted until it is 100 kilohertz. So that's the divide by blah blah loop. So it takes this BCD signal and generates the base frequency plus this value times 100 kilohertz. The base frequency is either 20 megahertz or 19.8 megahertz for reasons unknown. The summation loops, these three things, look like this, and I won't try and explain that because I only half understand it. Oh, this leveling circuit is, I think, this guy, the amplitude control. I haven't tried to understand this at all. The value that you type in for dBm on the front panel goes into here, and also the amplitude sweep comes into here. So this thing is that and the mixer. So you can see how, vaguely, how it generates the correct output frequency. I hope that explains that. That's as well as I understand it anyway. Moving on to the digital section. Remember when I opened that unit, I was struck by its similarity to a PDP-8S mini computer that I'd seen long ago, with all its cards in rows. And so when I was skimming through the service manual, this diagram here caught my eye, because it looks a lot like the micro instruction engine of a computer, and in fact that's what it is. It's got an address register that provides an 8-bit address to a ROM, which is the control store containing the microcode, and out comes 48 bits. Like most microcontrolled systems, it's quite a wide output with maybe not so many locations, only 256, but 48 bits wide, and 20 of them are shown here. This is just the address selection part, so it's not all of the ROM output, but 20 of them go through multiplexers, storage, this qualifier selector, and ultimately that all comes back to the address storage, where every time that control clock ticks, a new 8 bits are loaded into the address latch and a new value is presented to the ROM, and then these outputs change. And that's all controlled by not only the values inside the ROM, but also 27 qualifier signals, which are from the front panel controls, possibly some other signals within inside the machine. So as they change, it affects what the next address will be in the ROM. So depending on circumstances, it'll branch to different places in the ROM and execute different code. And out of that also comes instructions to the processing part of the computer, plus the remainder, another 20 odd bits out here that aren't shown, that also go into the computer part. It's similar to a microprogram computer, but not exactly. It doesn't take instructions from main memory, machine instructions, and then execute microcode for each of those. But if it did, that the opcode fetched from the memory for the machine instruction would affect this address storage to tell it where to start executing micro instructions from. Probably have some of this stuff as well, but the address would be loaded differently. So this thing is more of a state machine. it just screams around in a loop. This control clock toggles, I think, at about 125 kilohertz. That's, I think, 2 megahertz divided by 16. And it just latches whatever's on here every 8 microseconds or so. This control clock will toggle and a new value will be loaded in. So it just does that all the time. And which state it moves to each time is controlled by these qualifiers. So it's just a state machine, endlessly runs around in circles, waiting for values here to affect its operation. And part of its output is these instructions. Here's the overall diagram of the digital section. That part we were looking at before is just this section here. So it has inputs from the front panel, which go into those qualifiers. It produces outputs, which go to the display and to the frequency synthesis section, controls the frequency, and also to the amplitude control. And the instruction, that 5-bit instruction word plus whatever else, goes into this section, which is the CPU, Control Processing Unit, not Central Processing Unit. And it's a real computer. It's got a whole bunch of registers, A, P, Q, R, M, some random access memory, an arithmetic logic unit. So it's a proper computer. It doesn't operate in parallel like most computers do these days. It's bit serial, so every tick of that clock to the state machine control, there's 16 pulses here that running at 2 megahertz that shift bits around inside all these registers. So these aren't parallel registers, they're shift registers. So I hope that was vaguely understandable, my explanation of the frequency synthesis and the control computer. I hope you found all of this interesting. I'm not going to do any fiddling around with trying to adjust that frequency reference on the back in this video, because it's gone on long enough and I just want to get this thing out and worry about that other stuff later. So, yeah, hope you enjoyed. Don't forget to smash that like button before you watch the video, and I'll catch you later.